Hey there, students. Welcome to part two of finding the extreme value of functions analytically and also graphically. All right, so in number two, just like in part one, we're going to find out critical points, sketch the graph on the specified domain, and then we're going to use our results from A and B to find the location, description, and value of the extrema. And then in part D, we're going to see the applicability of the extreme value theorem. All right, so for number two, we have the function y equals 3 minus the absolute value of x on the closed interval. Actually, it's not closed interval. From -2 all the way to 1. All right. So -2 inclusive, +1 excluded. All right. Okay. Let's start with the first part. Part A. We have to find the critical points. Critical points. Now, what are the critical points? The critical points are the points where the first derivative y prime of the function is either equal to 0 or does not exist. And we know when the derivative does not exist, right? When you have a corner cusp, discontinuity, or a vertical tangent, okay? All right, so to do this, what we're going to do, let's rewrite the function y is equal to 3 minus the absolute value of x. We need to find the first derivative. So we have y prime. Y prime is equal to, well, let's see, 3 minus the absolute value of x prime. Let's write that again. 3 minus the absolute value of x prime. Okay? So there's a little complication here. We have to differentiate an absolute value function. So how do we do that? Well, if you remember the formula for differentiating an absolute value, you can just use it. The formula is the absolute value of x prime is equal to x over the absolute value of x. Okay, so the derivative of this portion right here is going to be negative x over the absolute value of x. That's if you remember the formula. But what if you don't remember the formula? What you have to do is just express this absolute value as an exponent. Okay, so y prime, we can write this as 3 minus the square root of x squared prime. Okay, this is just based on the fact that the absolute value of x is the same thing as the square root of x squared. Okay, so if you don't remember the rules for differentiating absolute value, just express the absolute value quantity like this, and then we can go ahead and find the derivative of this function. All right, so let's go ahead and find the derivative. Y prime is going to be equal to derivative of 3 is 0 minus, now we're going to use the chain rule here. Okay, when we're differentiating the outer function, which is the radical function, we're going to have 1 over 2 root x squared. We know that's the case. That's a shortcut of applying the power rule to a fractional exponent of 1/2. We know that d dx of the square root of u is equal to 1 over 2 root u du dx. Okay, so that's for the outer function, the square root of x squared. Now we're going to multiply that by the derivative of the inner function. U in this case is x squared. Derivative of x squared is 2x. Okay, so we have y prime is equal to negative 2x over 2 root x squared. And then these two 2's divide out. This 2 goes here 1, 2 goes here 1. And that becomes negative x over, now the square root of x squared can be written as the absolute value of x. Alright, so there goes the derivative. Now, to find the critical points, we're going to divvy it up into two cases. First one is we'll have to find where the derivative is equal to 0. And then next we have to find where the derivative does not exist. Okay? Alright, so when does this function attain a value of 0? So we have to solve the equation negative x over the absolute value of x equals 0. So when does it attain a value of 0? We can multiply by x's here, or else we introduce extraneous solutions. So how about we simplify this expression right here? We can rewrite this as negative x over plus or minus x. So when is this equal to 0? If you divide plus or minus, if you divide minus by plus or minus, you're going to end up with minus or plus, which is the same thing as plus or minus. So this becomes plus or minus 1 over 1 equals 0. So when is plus or 1 minus 1 equals 0? The answer is never. Okay? So what does it tell me? It tells me that this function never has a horizontal tangent. The derivative never attains a value of 0. This equation right here has no solution. Okay? All right, how about, is it possible that the derivative does not exist? And the answer is yes. Where does the derivative not exist? All you have to do is find what makes this function undefined. So we can just extract the denominator, which is absolute value of x, and set it equal to 0. Okay, because we know when the denominator attains a value of 0, this expression becomes undefined. So how do we solve this piece right here? We can just rewrite absolute value using plus or minus. So we write this as plus or minus x equals 0. Okay, and then this tells us that x is equal to plus or minus 0, but 0 has no orientation, so x equals 0. Okay, so that's the only critical point that we have in this problem. Okay, so for part A, we have a critical point right here, critical point of x equals 0. Okay, even though it's a critical point, that doesn't guarantee that it's an extrema. Okay, we have to take a look at the graph in order to know for certainty if it is an extrema or not. So that's that for the A part. Now let's shift our attention to the B part. Let's make a sketch. So let's sketch the graph. Okay, I'm going to partition my workspace. Let me move it down a little bit so I can see everything at once. Okay, so how does a graph of 3 minus the absolute value of x look like? That's the question. So B, we're going to graph. We're going to try and sketch the graph of y equals 3 minus the absolute value of x. Well, this graph is the absolute value function reflected. It's normally facing up, right? But with this minus, it's reflected down and it's shifted 2 units up. I mean, shifted 3 units up because you have the plus 3 component here. All right, so we take our typical absolute value function, which opens up like this. We reflect it down and shift it 3 units up. That would give us what this graph looks like. Okay, so let's go ahead and graph it. A symmetric with respect to the y-axis. So I can put the y-axis at the center. So the graph, the derivative already tells us that on the left side, the slope, to the left of 0, the slope is -1. To the right of 0, it's +1 to the left of 0, and then it's -1 to the right of 0. So let's go ahead and graph that. So it goes up 1, 2, 3. That's where the vertex resides. So down 1, left, down 1, back 1, down 1, back 1. It stops at, where does it stop? Oh, it stops at our interval is from -2, so this right here is -2, all the way to 1. Okay, so right there we have, let me go back and see, okay, we have a closed circle. We have a closed circle here, and then we have an open circle here. All right, and then let's draw our reflected V that has been shifted 3 units up. Looks something like that. Okay, so there goes the graph of the function. It helps us to really see the behavior of the graph and also how to classify and locate our extrema. Okay, so now we have the tools to advance to part C. So for part C, we are to use the results here to locate and describe our extrema and also state their value. Okay, so for part C, we have to start with the, let's take a look at the critical point. In this graph, the critical point is at x equals 0. So that clearly looks like an extrema. So we're going to look at the critical point. So this is part C. We're going to look at the critical point. Critical point x equals 0. Okay, so for this one, we're going to evaluate f of 0, which is equal to 3 minus the absolute value of 0. We're going to plug this value into the original function to see the output. So if we work this out, we're going to get simply 3. Okay, so this point right here, that's the value that we're dealing with. So what we have here is a local. We have a local and absolute max of 3 at x equals 0. You can clearly see that on this graph. Let's go ahead and label that. So this point right here, that's a critical point and is also an extrema. This happens to be the local. In the neighborhood, it's the biggest, and also in the entire interval, it's also the biggest. So local and absolute max, and it happens at the point 0, 3. Okay, let me erase that real quick. It happens at the point 0, which is a location, and 3 is the value of the relative extrema, which happens to be the absolute or global extrema also. All right. Okay, now we're going to take a look at the endpoints. Remember, you always have to look at the endpoints, included endpoints in the specified domain to determine your extrema, okay? So which x are we looking at here? Now you have to be careful because in this graph, there is only one endpoint that's included in the domain. So the only endpoint included is -2, so we're going to be looking at x equals -2. All right, so let's find out the value of this extrema. F of -2 is equal to 3 minus the absolute value of -2, which equals, this is 3 minus 2, which equals +1. Okay, so that's this point right here. You can see traces to +1. So this happens to be a local and absolute minimum value of +1, and it happens at x equals -2. All right, so let's go ahead and label that on our graph. So this right here is your local and absolute minimum, and it happens at the point -2, 1. All right, so that's that. Now how about this point right here? Well, this point is excluded from the graph. Okay, there isn't any extrema at this point because you have an open circle there. All right, so that's basically that for our extrema. Now let's shift our attention to the D part, which is the applicability of the mean value theorem. Of the extreme value theorem, sorry. So can we apply the extreme value theorem here? The answer is absolutely not, because it violates one of the initial conditions, which is that the interval be closed. Okay, so since the interval is not closed, we cannot apply the extreme value theorem. Okay, so for part D, the extreme value theorem, the extreme value theorem does not apply, does not apply since the interval is not closed. Okay, since the interval is not closed. All right, so that's that. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking here so you can get updates to the next installments of this review series. And also post a comment to let me know what you think about this presentation. And if you liked it, you can give me a thumbs up. I really appreciate it by clicking like. More clips can be found on math.serve.com/calculus. Thanks again for watching and have a wonderful day.